Let's talk about energy, specifically the different kinds of energy that are out there. The first one that we're going to talk about is kinetic energy. Any object that is moving has kinetic energy. So for instance, let's say if we have a block that is sliding across a horizontal surface. If that block has some kind of speed attached to it, it has kinetic energy. Kinetic energy is proportional to the mass of an object and the square of the speed of that object. Now, some objects have the ability to rotate. So think of a wheel that's spinning. In this case, it has rotational kinetic energy. Now, another type of energy is potential energy. This is a type of stored energy as opposed to objects in motion. A good example is, let's say if we have a ball, or rather a block on this hill. This block has the ability to slide down. When it's sliding down, it's going to have kinetic energy. But if it remains at rest at that position, it has the ability to fall. Or, let's say if we put a ball above ground level, that ball has the ability to fall. So it has stored potential energy. Potential energy has to do with the position of one object relative to another. So to illustrate this, let's say this is, let me draw a better picture. Let's say this is the Earth. And let's say this is object 1 and object 2. Both of these objects are above ground level and they have the ability to fall. So they both have potential energy. Now, which of these two objects have more potential energy, number 1 or number 2? Number 2 has a greater amount of gravitational potential energy because it's at a higher position. So when it falls, by the time it hits the Earth or it hits the ground, it's going to be moving at a higher speed compared to object 1 if we neglect air resistance. Gravitational potential energy is equal to the mass times the gravitational acceleration times the height. So as we increase the height of the object, the gravitational potential energy increases. So because object 2 is at a higher position than object 1, it's going to have a higher potential energy. So this object wants to move from a high position to a low position. As it does so, energy will be converted from potential to kinetic. Now, notice that the gravitational force is directed downward. When an object, when it moves in the same direction as the force that gives its potential energy, that potential energy is going to decrease. Now, if we were to move this object opposite to the gravitational force, the potential energy will increase. If we were to move the object in the direction of the gravitational force, the potential energy will decrease. I'm going to talk about that concept throughout this video as it relates to other forms of energy, but remember this. So in this situation, we have a gravitational field. If you were to move the object opposite to the direction of the gravitational force, the potential energy is going to go up. If you were to move it in the direction of the gravitational force, the potential energy will go down. Now, this situation is similar to another type of potential energy called electric potential energy, in which case the potential energy is determined by the relative positions of charged particles. So let's say we have a charged plate, a positively charged plate, and we have two charges. We'll call this charge number 1 and charge number 2. Looking at these two charges, let's say they have the same magnitude of charge. Which one will have a higher electric potential energy? Charge 1 or charge 2? What would you say? Both of these charges will feel an electric force that's going to propel them away from the charge plate. Now, charge 1 is closer to this plate, so it's going to have a higher electric potential. Charge 2 is further away from it, so it's going to have a lower electric potential. If we were to move charge 2 opposite to the direction of the electric force, if we were to bring it closer to the charge plate, the gravitational potential energy, not gravitational, but the electric potential energy will increase because we're moving it in the direction opposite to the electric force. Now, if we were to move the charge in the direction of the electric force, the electric potential energy will decrease, much in the same case as the gravitational potential energy in the last example. So you can see the similarities here. So electric potential energy and gravitational potential energy, they're very similar. If you look at the formulas for gravitational potential energy, it's mgh, and if you compare that to the formula for electric potential energy, it's negative q, that's the charge, times the electric field, times the height, or the distance between the charge and the charge plate. So looking at these two formulas, you can see the similarities. Instead of mass, here we have charge. Instead of gravitational acceleration, here we have the electric field. And these two are similar. H and Y, they're both basically distance, but in a vertical direction. Now, there are other different types of potential energy. The next one is the elastic potential energy. This is commonly associated with springs. So let's say we have a spring whose natural length goes up to this point. Now, if we were to apply a force on this spring to compress it, we're going to transfer energy to the spring. In fact, that's what a force can do. Whenever a force is applied to an object, it's transferring energy to that object. So as we apply a force to compress the spring, we're storing up potential energy in this spring. Let's call this situation A and situation B. Which one has more stored elastic potential energy? Situation A or B? The more we compress the spring, the greater the amount of stored energy in that spring will be. So the answer will be situation B. The potential energy stored in a spring is equal to 1/2 kx squared. K is a spring constant with the units newtons per meter. So a spring constant of 400 newtons per meter tells us that in order to compress the spring by 1 meter, we need to apply a force of 400 newtons. X is the distance between the original natural length of the spring and the amount by which we compress it or by which we stretch it. So if you stretch the spring, that spring will also have stored potential energy, the same as if you compress it. So that's another way in which we could store energy. We can store it in the form of a spring. We can store energy by moving an object to a high position. And we could store it by moving charges from one position to another. So going back to this scenario, If we were to move the charge, if we were to apply a force and move the charge to a position that's closer to the positively charged plate, we're storing energy. We're increasing the electric potential energy of this charge. If we were to move that positive charge away from the positively charged plate, we're decreasing the potential energy of that charge, and it naturally wants to move away from it. Now the reverse is true if we had a negative charge. The negative charge wants to go closer to the positively charged plate. So if we were to move it away from the positively charged plate, we would be increasing its potential energy. We're basically storing energy into the system. The electric charge feels an electric force that wants to accelerate it towards the positively charged plate. So if we were to move the charge opposite in the direction of that electric force, we're increasing the electric potential energy of that charge. So in other words, we're storing energy in that system. Now there are other forms of potential energy. Another example is chemical potential energy. So think of the energy that's stored in a battery. That energy is stored in the form of chemical potential energy. Now, once we connect this battery to a circuit, let's say if we attach it to a light bulb, we can release that chemical potential energy and convert it to light energy. This will be converted to not only light energy, but heat energy as well. So electricity that is flowing from this battery to the light bulb is the mechanism by which energy is transferred from the battery to the light bulb. Now there are other things that store chemical potential energy. Think about the foods that we eat. Think about rice, beans, chicken. We derive energy from eating these foods, which allows us to function, to move, to run, to work out. We talked about batteries already. They can store chemical potential energy. But even certain molecules, like hydrocarbons, think of the gasoline in an automobile. We use gasoline to power our vehicles. We use the internal combustion engine to convert the energy that's found in gasoline into mechanical energy, which can drive the vehicle forward. Or we could use that mechanical energy to basically drive an alternator, which will convert that mechanical energy into electricity, which will charge the car battery. So chemical potential energy is something that we tend to make use of a lot in our daily living. Now, there are other forms of potential energy that is found in nature. A good example has to do with a phase change. So let's say we have a liquid, and here are the molecules in this liquid. When the liquid freezes into a solid, something happens. The molecules in a solid, not for all solids, but in the case of most solids, the molecules tend to be closer to each other compared to a liquid. And so when you freeze a liquid, you're bringing the molecules closer together in most cases. Water is an exception. And a lot of times when you do this, energy is released, particularly heat energy. Now, a phase change occurs without a change in temperature. So let's say we have this liquid at 45 degrees Celsius, let's say that is the melting point of the liquid, it can freeze at that same temperature. So this is a form of potential energy. That energy can be released without a change in temperature. As the molecules or the atoms move closer together, and as they freeze from a liquid to a solid, that's an exothermic process. Energy is released. Think about steam. When steam condenses into liquid water, energy is released. And this could happen without a temperature change. Steam at 100 degrees Celsius, when it condenses to liquid water at 100 degrees Celsius, it's going to release heat. So that's a form of stored energy that is in the molecules of steam. The reverse is also true. Let's say if you were to release water in, let's say, a very hot and dry environment, that water is going to evaporate. Evaporation has a cooling effect. It's endothermic. And so when water evaporates in a very hot, dry environment, it's going to absorb the heat in that hot, dry environment, cooling it down. This is known as evaporative cooling. So molecules, the position of one molecule relative to another has potential energy, as we see here. In the case of a typical liquid, as the atoms get closer to each other, converting the liquid into a solid, energy is released. So this is a form of positional potential energy, where the potential energy is based on the relative position of the atoms with respect to each other. Another example of this has to do with pressure. So imagine if we have a container with gas, pressurized gas, let's say at 100 atm. That's atmospheric pressure. And outside of that, we have normal atmospheric pressure of 1 atm. So here we have a region of high pressure in the inside. On the outside, we have a region of low pressure. Now the gas particles in this container, they're going to be very close to each other because they're forced into a small region of space. And so when you force gas molecules into a small region of space, the pressure is going to go up. Outside of that, the pressure is low. So the gas particles, they're more spread out. So in this situation, now for gases and liquids, the situation is different. In this case, we're dealing with a gas. When the atoms are closer together, you have more potential energy compared to when the atoms are further apart. So here we have a situation of high pressure and high potential energy. Once we open this valve and we release the stored gas molecules, the gas particles, they're going to force their way into this opening. And as they do so, they're going to exert a force on this object. As they exert a force on that object, they're going to do work on it. And so this system has stored potential energy because once we release it, work can be done by this pressurized gas. As the gas particles move from a situation where the atoms are close to each other to a situation where the atoms are further apart, energy is released. So if we want to store energy in the form of pressure, we need to apply a force against the direction in which those gas particles want to go. So if we were to take a pump and we were to force the gas particles into this small container, increasing the pressure, we're basically increasing the internal energy of the system. But once we release that gas and let it flow in the direction from high pressure to low pressure, energy is going to be released. If you notice, things tend to flow in that order. Energy likes to flow from a high position to a low position. So like these gas particles, the gas wants to flow from a region of high pressure to a region of low pressure. In the case of this object, it wants to fall from a high position to a low position. Even electricity. Let's say if we were to have a resistor, and at this point we have an electric potential of positive 50, and here we have an electric potential of 10 volts, positive 10 volts. Conventional current wants to flow in the direction of high electric potential to low electric potential, just as water wants to flow from a high position to a low position. Now the same is true with heat. Let's say if we have a region of high temperature, let's say this object is hot, it's at 100 degrees Celsius, and this part is cold, let's say it's at 10 degrees Celsius. So here we have a region of high thermal energy. Here we have a region of low thermal energy. Heat is going to flow from hot to cold. Heat is the flow of thermal energy. And that's usually how energy will typically flow. It usually flows from something high to something low. Now, you might be wondering, what exactly is thermal energy? When you're dealing with solids, the thermal energy inside a solid has to do with the vibrational energy of those molecules. If you were to increase the temperature of the solid, those atoms in that solid, they're going to vibrate more. Their vibrational energy is going to increase. When you're dealing with gases, the situation is a bit different because gases, they're free to move. So if you were to increase the temperature of a gas, the gas particles, they're going to be moving faster. You're going to increase the kinetic energy of those gas particles. And there's a formula for this. When dealing with gases, the average kinetic energy is equal to 3/2 times Boltzmann's constant times the temperature. So if you were to increase the temperature of the gas, you're increasing the thermal energy of that system, and you're also going to increase the kinetic energy of those individual gas particles, which means those gas particles are going to be moving faster. There's something called the root mean square velocity of a gas particle, and it's equal to the square root of 3RT over m, where T is the temperature, m is the molar mass. So heavy gas particles, they tend to move slower, but a gas particle or a sample of gas at a higher temperature will have gas particles moving at a greater speed. So when talking about the thermal energy of a solid, typically you're talking about the vibrational energy of the molecules in that solid. When you're discussing the thermal energy of a gas, a lot of times you're talking about the speed at which those gas particles are moving. Because the hotter that gas sample is, the faster those gas particles will be moving, the more average kinetic energy they will have. Now the next thing we're going to talk about is wind energy. Now wind, even though you could use wind to basically generate electricity, in the case of, let's say if you have like a windmill or a wind turbine, wind is more of a force. So wind is basically like the force that pushes air molecules from one place to another. But anytime you have a force, you can derive energy from that. Because forces, whenever they act on an object, they can transfer energy to that object. So energy can be derived from wind, but we can't really say wind is an energy when it's really a force. The next thing we're going to talk about has to do with light energy. Actually, before we talk about light energy, let's talk about sound energy. Now, sound is a wave. More specifically, it's a pressure wave. So let's say you have a speaker and it emits a sound. What's really happening is you have regions of compression and expansion in the gas particles in the air. So in one area, the gas particles are very close to each other. So this is a region of high pressure. This is a region of compression. After that, the gas particles are more spread out. That's a region of low pressure. So that's a region of expansion. And following expansion, you have compression. And so in a sound wave, you have this alternating pattern of pressure. You have regions of high pressure followed by regions of low pressure. So sound is a wave. More specifically, it's a pressure wave. So here's the region of high pressure, and then here you have a region of low pressure, and then high pressure, and so forth. Now, a wave is basically a disturbance that can travel through a medium like water, or it could travel through air, or it can even travel through empty space. So a wave is basically a disturbance that can transfer energy from one region to another. But when dealing with sound, sound doesn't really transmit through empty space. It could be transmitted through air, or it could be transmitted through a solid or even a liquid. For instance, let's say if a train is coming, likely you can hear the vibrations on the ground. You can hear the sound traveling through the ground. Sound can also travel through water. Think of sonar, just as they can travel through air. But in empty space, you don't have a lot of particles where you can have regions of compression and expansion, so sound really doesn't travel in space. But nevertheless, sound is a wave, and waves can transmit energy. So that's what sound is. It's basically a pressure wave. Now, we also have light energy. Like sound, light is a wave as well. And as a result, it can transfer energy. So think about the light that we receive from the sun. Because of that, we can get electricity from the sun. Let's say if we have a solar cell, let's say we lay it out in the sun, that solar cell will convert light energy into electricity, and we could store that electricity in a battery. Let's say if we have a tree. Trees can also store light energy in the form of chemical potential energy. Going back to the first example, this solar cell will absorb light energy and convert it to electricity. As the electricity flows into the battery, that battery is converting the electric energy into chemical potential energy. In the case of a tree, the tree can convert light energy into chemical potential energy by means of a process known as photosynthesis. In photosynthesis, the leaves of the trees will absorb carbon dioxide from the air, and they're going to pull up water through the roots. They're going to pull up water from the ground through their roots in this reaction. And using light energy, they will convert carbon dioxide and water into a sugar known as glucose. And at the same time, the trees will release oxygen in the air for us to breathe. So this is photosynthesis, the process of converting light energy into chemical potential energy in the form of a high energy hydrocarbon. So light carries energy, as we could see. And light is basically a wave. You could think of it as a particle too. So light is associated with particles known as photons. A photon can behave as a particle, but it can also behave as a wave as well. There's something called the particle-wave duality. Even electrons can do this too. Electrons can behave as particles, but they can also behave as waves. But when talking about light, light has an oscillating electric field, but it also has an oscillating magnetic field, which is perpendicular to the electric field. So because of the oscillating electric magnetic fields, light is an EM wave, an electromagnetic wave. Now there are other types of electromagnetic waves other than light. We have radio waves, microwaves, infrared radiation, visible light, ultraviolet rays, X-rays, and gamma rays. And beyond that, cosmic rays. As it moves to the right, the energy of these radiation or forms of radiation increases. The frequency also goes up, but the wavelength decreases. So gamma rays has a shorter wavelength than radio waves. Going to the left, the energy decreases. Radio waves have the lowest energy. They have the lowest frequency, but they have the longest wavelength. So that's another type of energy that we can discuss. Now, there's also mechanical energy. When talking about mechanical energy, it's the sum of kinetic energy and potential energy. So an object in motion has mechanical energy. An object that has the ability to fall, let's say an object at high position, also has mechanical energy.